In this section, we're going to talk about limits and continuity. We've talked about limits and continuity for functions of a single variable since Cal 1, and even to some limited extent even before calculus, although the formal definition does come about when we learn the concept of a limit. But now that we have functions of multiple variables, we need to carefully consider what is meant by a limit and continuity for these multivariable functions and make any adjustments as necessary. So let's begin with the basic definition. Let's begin with a point. Let x naught comma y naught be a point in the plane. And let delta be a positive real number. Not negative, not zero, specifically positive, greater than 0. Then, the set of x comma y such that the square root of x minus x naught quantity squared plus y minus y naught quantity squared is less than delta is called the delta neighborhood, or sometimes called the delta ball, about the point x naught comma y naught. Okay. This will serve to replace the interval on the line. Whenever you have the number line, you can have a point on that number line which we can call, x naught. Now you can say, okay, I want an interval around that point. Okay, well there you go. There's your interval. Okay. Here I'm going to go ahead and not include either endpoint, so this will be called the open interval. About the point x naught. Okay, so that's just an open interval the way you're used to on the number line. What the delta neighborhood or the delta ball does is it replaces the concept of an interval but on a plane. So what this says is you have a point on the plane. Doesn't matter where the point is, I'll say it's right there. There's my point x naught comma y naught. Okay, now pick a number, delta, that's positive. Not 0, not negative, but any positive number. So 6, 1/3, 0.0000009. Whatever that might be. Then what we're looking for is we're looking for all the points. You say, well, what is this thing? That's the distance formula. That's the distance between x and x naught, y naught. Oh yeah, so this is the point. This is the distance between this point x naught, y naught, and some other point, which we're calling xy. What we want is we want the set of all of these points whose distance away from x naught, y naught is less than that number delta. So let's say that my number delta was 1, for example. Okay, so that's 1. Then all the points that are within 1 step away from x naught comma y naught, that's the neighborhood around that point. Instead of having an open interval, you have an open neighborhood. It's a little disk instead of a little interval. Okay. We're going to need a few other definitions for the main part of this section to make sense. So let's continue on to our next definition. So let's take a region in the plane. Let's call it R for region because I'm very original when it comes to labeling stuff. Let R be a region. Let R be a region in the plane. And x naught comma y naught be a point in R. X naught comma y naught is called an interior point. Of the region R, if and only if there exists a delta neighborhood one of these things up here about the point x naught comma y naught that is contained entirely in R. X naught comma y naught is called the boundary point of R. It's called the boundary point of R. If every delta neighborhood about the point x naught comma y naught contains points in R and points not in R. Okay, so here's a region in the plane. Call it R. This point right here is an interior point. Why? Because I can find some little neighborhood that is entirely inside of R. Here's a neighborhood around the point, and the entire neighborhood is inside of R. You can be close to the edge, and that's fine. You just need a smaller neighborhood. Here I was able to choose a pretty big neighborhood. Over here, that's also an interior point, because even though I can't choose a neighborhood that's that big, as long as I take a small enough neighborhood, that's fine. These are all interior points. Okay? A boundary point would be, well, something on the boundary, something on the edge. Because here, no matter how big or small I make my neighborhood, I have some points that are inside of R and some other points that are not inside of R. So here, both of these would be interior. And this one would be a boundary point. All right. Our next definition. Let's take a region in the plane. Let R be a region in the plane. If every point x naught comma y naught in the region in R is an interior point, then we say R is an open region. if R contains all of its boundary points, then R is said to be closed. One important note, these are not opposites of each other. Just because something is not open does not make it closed. Just because something is not closed doesn't make it open. You have some things that are neither open nor closed. And, although we don't discuss them in this course, there are some exotic spaces which are both open and closed. They're a bit strange. In any event, here, note, some regions are neither open nor closed. These are not opposites. That naming is a little unfortunate because usually in everyday parlance, open and closed would be opposites. But here they're not. It's possible to have a region that's neither open nor closed. Right. A visual example of that. Here's a region. When we use a dotted line, that means those points aren't part of the region, just the stuff inside. This is an open region because every point that I can pick is interior. That one, oh yeah, that's interior because it's got a little neighborhood that's inside the region. Pick one really close to the boundary, that's fine. I just need something that's small enough, right? I just need a neighborhood that's tiny. The neighborhood doesn't have to be big. I just have to be able to find one. And then you say, well, no, because what if you just pick this point right over here? Then that one would not be an interior point. Right, but that's not in the region. Remember, the dotted line means you're including the stuff inside of this wall, but not the wall itself. So here, every point is an interior point. All the points that would be boundary points aren't actually part of the region. This is analogous to the, on the number line, an open interval, something like 2, 3. Here, you want everything between 2 and 3, but not including either of the boundaries. So that would be an open interval. Here, you want all the stuff inside of the region, but not the region, not the boundary itself. So that would be an open region. Open interval. And the analog on the plane is the open region. Closed would be something like this. Any point that would be a boundary point is included in the region. So for example, this right here would be a boundary point because it's a point that includes things in and out of the region. And so would this one, and so would this one, and so would this one. Well, yeah, but notice that every point that I'm saying, oh yeah, this would be a boundary point, it's just a point from my region. So here all of my boundary is included. That's the analog to the closed interval. On the number line, you can have closed intervals. Here, you can have closed regions. And then, of course, there are regions which are neither open nor closed. For example, this. Here, this one is not open. Why? Because I have a point that is not an interior point. So not interior. Okay, so it cannot be open. But it can't be closed either. Because here, this right here, this is a boundary point. It includes points that are inside and outside or in the neighborhood around it. No matter how small I make that neighborhood, I'll have some points that are in and some points that are out. But here, that's not part of my region. The dotted line means that I go up to that line, but that line is not part of my region. So here, I don't include all my boundary points. In particular, I don't include this one. I don't include this boundary point. So that means, yeah, it's not open, but it's also not closed. And on the number line, the analog would be something like this, where, yeah, that's not closed because it does include this. It's not closed because it doesn't include this endpoint, but it's not open because it does include this endpoint. That's the analog in the plane. All right, so now we have our three small definitions. What does it mean to have a delta neighborhood? It's a little disk around the point. What does it mean to have an interior point? You can find a little disk that's entirely inside the region. If you have little disks that are partially in and partially out, then those would be boundary points instead of interior points. What does it mean for a region to be open? All the points are interior points. Closed, all your boundary points are included. It's possible not to be neither. With those three definitions established, now we can give the main definition for this section. Let's define how a limit works for a function of two variables. Definition. Let's let f be a function of two variables. It's going to be defined on an open disk centered at some point x naught comma y naught. Okay, so you have a function of two variables. It's defined on an open disk. Okay, we know what open means. All the points are interior points. It's a disk. You can also think of this as an open neighborhood that is about this point, that's centered at this point. Okay. It's defined everywhere inside of this disk, except maybe at the point. If it's not defined at the point, that's fine, at the center. But everywhere else inside the disk, it must be defined. Except maybe at x naught comma y naught. Finally, let's let L be a real number. Let L be a real number. Doesn't matter what it is, just some real number. It can be 0, it can be positive, negative, doesn't matter. Then, the limit as x comma y approaches x naught comma y naught of f of x comma y equals to L if and only if, and now this should sound very familiar, we're back in Cal 1. If and only if, for all epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than the square root of x minus x naught squared plus y minus y naught squared is less than delta, implies that the absolute value of f of x comma y minus L is less than epsilon. All right. Let's dissect this. First of all, notice how similar this is to the definition of a limit of a single variable function. Okay, but what does this say? All right, well here this is just some symbology, right? Some terminology. The limit as x comma y approaches x naught comma y naught of f of x comma y equals to L. That's just the way we write it. That's just the notation. What this notation means is, okay, for all epsilon greater than 0. Now here, that's just some positive number. But generally, when you use epsilon, the implication is that it's a very small positive number. Yeah, it could be 1 million, but it's probably 0.0000001, something very small. There exists a delta greater than 0. Same thing, epsilon and delta, they're both positive numbers, but it's implied that they're both small numbers. Such that, okay, well, we saw this as part of an earlier definition. Square root of x minus x naught squared plus y minus y naught squared is less than delta. Square root of x minus x naught squared plus y minus y naught squared is less than delta. This is a delta neighborhood. Okay, so for all tiny numbers, there exists some other number such that if you have your point within a delta neighborhood, right, these are your 2 points, x comma y is said to be approaching x naught comma y naught. Oh, okay, well that's what it means to approach. That means that they're really close to each other. Oh, how close? Oh, they're both in the same little neighborhood. Okay, so they're in the same little neighborhood. What about it? Well, if they're in the same little neighborhood, that implies that the result that I get by plugging in this x comma y into my function and this value of L are also very, very close. Because remember, these are very tiny numbers. So one more time. You give me a tiny number, and I bet you I can find you some other number. What is that other number telling me? It's telling me that as long as my point and your point are within that distance of each other, then plugging in my point into my function gives me as close as you wanted me to be to that number there. You wanted me to be that close? Okay, I could find a neighborhood that makes me that close. So let me write that actually. Note, and again, this is not at all formal. This is formal, but basically, if the limit exists, then you can find a little disk, a little neighborhood around your x naught y naught on which f of xy is as close as you like to L as long as xy is in that little disk. That's basically what that's saying. Another thing to note is when you looked at a limit in a function of one variable. Okay, so here you have a function y equals f of x. Okay, so thinking back to Cal 1. When you took the limit, there were really two limits. You can take the limit from the left or the limit from the right. And as long as both of those agreed, then yeah, that was your limit. However, if you had something like this, where your limits disagreed, coming in from the left and coming in from the right, your limits were different from each other, well then your limit did not exist. All right, so you have a function of one variable, then you're only considering that variable as it approaches your value. So let's say this is your x naught, and again that's your x naught. Here you'd want the limit as x approaches x naught of f of x is equal to L. Oh yeah, as my x gets closer to x naught, and I can go from either from the left or from the right, then my y value is getting as close as I want to being the value L. On the other hand, over here, that means that my limit as x approaches x naught of f of x is undefined, does not exist. Why? Because I never get close to any one number. If I come from the left or if I come from the right, I get different results. Okay? Note that on a function of two variables, that means that my domain is no longer just the x-axis, my domain is the entire plane. So now I have to consider not just coming in from the left or from the right, but from every direction in the plane. Meaning, let's say this was our function, some surface, right? You give me an x, y value, and I give you a z value. Okay, z equals f of x comma y. Oh, I guess I should have drawn that a little bit bigger. Something like this. Over here, I only have to worry about what happens as I'm approaching x from either the left or the right. But now I'm trying to approach not just x, but a specific x comma y on the plane. So that means I have to consider not just what happens from the left or from the right, but also from this direction, this direction, this direction, this direction, this direction. That becomes quite a bit more complicated. So although the definition is very similar in nature, from a practical standpoint, it does seem to be a bit more involved, considering it from so many different directions, rather than just the typical, oh, left-sided limit or right-sided limit. So let's talk about how that's going to work. First, let's consider one entirely by definition. Just like in Cal 1, yes, we can do it by the definition, but also there's some nice properties that allow us to forgo that for certain nice functions. However, we should still see what the function is, what this looks like by definition. All right? So let's see here. Let's verify that the limit as x comma y approaches the point 1 comma 0 of x is equal to 1. And we'll do this by definition. All right. Let 0 less than square root of x minus x naught squared plus y minus y naught squared less than delta implies that 0 less than square root of x minus 1 squared plus y squared. Here we're using x minus x naught and y minus y naught. But since y naught is 0, here instead of writing y minus 0, I'll just write y. Is less than delta. Then the absolute value of f of x comma y minus L, that's going to be, well, that's our function is just x minus our limit is 1. So here, that's your f of x comma y. It's that function x, the one you're taking the limit of, minus your L, that's your 1. That's equal to the square root of x minus 1 squared. Oh, that's starting to look familiar. That's starting to look like this one, which is less than or equal to the square root of x minus 1 squared plus y squared. These are, if y is equal to 0, those are equal. Otherwise, this would be greater than. So greater than or equal to here, which means this is less than or equal to. But then we began by saying, oh, less than delta. So if we just set delta and epsilon equal to each other, so if we set delta equal to epsilon, then if this is true, then that is less than this, which is less than this, which is less than this. But if you're saying delta and epsilon are the same, then this is less than epsilon. Then absolute value of f of x comma y minus L is less than delta, right? Basically, this is less than or equal to this one. You can cut out all the middlemen, which means absolute value of f of x comma y minus L is less than epsilon. Okay? If this is less than delta, well, then it's also less than epsilon, since we set delta and epsilon equal to each other, which verifies the claim. This should show two things. One, it should show that it's essentially the same argument that we see in Cal 1 for a limit. And two, that we didn't like doing that back then either. Here, this is showing, by definition, that if, in fact, this is less than delta, that does force this to be less than epsilon for any epsilon we so choose. Well, fortunately, there are all kinds of properties for limits that we have seen work well for functions of one variable in Cal 1. It turns out that many of those will work here as well. So let's take a look at what those would look like in a function of two variables. All right, consider the following. Let's find the limit we want the limit as x comma y approaches 1 comma minus 1 of x squared y over 1 plus xy squared. Okay. One of the things that we first learn as a shortcut to finding a limit is with a function of one variable, if you can plug in the value and you get something that's undefined or something that's, what's the word for that? Like 0 over 0, indeterminate. If you get something that's undefined or indeterminate, well, then that doesn't actually give you an answer. But if you can plug in the number and get just a regular real number, well, then that's your limit. Right? And we proved that in Cal 1. It turns out that that's still valid here. So here, note properties of limits of one variable functions still apply, including our very favorite one, including substitution. So here, if that can be substituted in and we get something that's undefined or indeterminate, well, then we get nothing. But in this case, that would be 1 squared times negative 1 over 1 plus 1 times negative 1 squared. After all, here x is going to 1. So if it actually reaches this without any problems, then x will equal to 1. So here this x and this x can be 1. Likewise, as long as this reaches this point without any problems, then y equals negative 1, there and there. So here this would be 1 times negative 1 is negative 1. Here that would be negative 1 squared, which is positive 1, times 1. Well, that whole thing is still 1, plus another 1 is 2. And there we go, there's our limit. Another example. Let's find the limit. we'll take the limit as x comma y approaches the origin, 0, 0, of 1 over x squared y squared. In this case, you can't do this, because if you plug in 0, 0, you get a nonsensical statement. Okay, well, then that doesn't work. Okay, so what can we do? Well, what you're doing is you're approaching the origin from somewhere on the plane. So, here's the origin, and you're trying to get to the origin from any and every direction. Okay? All right, well, one direction that I could approach from is I could approach along the x-axis. This is actually a nice trick. Here, I could approach from any and every possible direction, which is one of the things that makes this so complicated. Well, one of the directions that I could approach from is the x-axis. I like this one, though. And why do you like this one? Because if I'm approaching along the x-axis, that means y is equal to 0. So right here, if I approach, here, let's do it together. If we approach, 0, 0 along the x-axis, then that means that, okay, yeah, x is a variable. X is 1, 1/2, 1/4, 1/8, and so forth. But along this path, y is just 0. Okay, so then this limit is, oh, we don't have to worry about it as a 2-variable function. We can treat it as a 1-variable function. We can treat this as x comma 0 approaches 0 comma 0. Hey, we're setting y to a constant, 0. Oh, but well, in that case, it becomes pretty apparent what's going on. If x squared times, that would be 0 squared. Notice that's undefined. I'm not even talking about the limit. I'm just talking about this thing. So how can you take the limit of something that's undefined? No, you can't. Okay, so then that means here this limit does not exist. This part is undefined. So here this limit does not exist. This trick right here is nice, but it's a little misleading. You would never check all the different directions and say, oh yeah, I checked all the different directions and I get that the limit is equal to 12, or whatever. Because here, how many directions can you approach from? Infinitely many. How many lines are there coming out of the origin? Infinitely many. So here, to check all of them would literally take forever. You can't do that. Instead, what this is often used is, you can use this to, if you suspect that the limit exists, well, you have to find some way to confirm that. This is used if you suspect the limit does not exist. Because then, if you can find any one path where the limit does not exist, or even if it does exist but it disagrees, meaning, oh, the limit from this side would be 0 and the limit from this side would be 5, oh, well, then again, the limit would not exist. Just like in Cal 1, if the limit from the left is different from the limit from the right, then there is no limit. So here, this, where you're checking a few different paths, is best used, in fact, it's only used, if you suspect that the limit does not exist in the first place. If you suspect that it does exist, then that's not going to get you anywhere. Let's see that again. Let's go and find the limit. Limit as x comma y approaches 0 comma 0 of x squared minus y squared over x squared plus y squared squared. Okay. Now, right here, I suspect the limit does not exist. Well, why would you suspect that? Well, here I have 0 over 0. That's indeterminate. Okay, but still, that is the number 1. That is the number -1. So somehow that feels like, oh, too many different things are happening. This is indeterminate. This is +1. This is -1. Oh, but maybe the square will clean things up. Maybe being positive and being -1 is okay because of that square. Okay, so I'm not really sure. I suspect, however, this one does not have a limit. And again, my main reason is because this is got a denominator of 0. But that doesn't inherently mean anything. We've seen plenty of times where you can take a limit of 0 over 0 and get a perfectly good value. But here I'm going to go on a hunch. I'm going to say, okay, I think this limit does not exist. So let me check a path. I'm going to go ahead and pick the path along the x-axis. Okay, along the x-axis, that means y is equal to 0. Okay, so that would give me the limit as x comma y. Oh, well, I want y to be 0 because we're on the x-axis. So x comma 0 approaches 0 comma 0 of, okay, so again, y is no longer variable, it's just 0. So that would give me x squared minus 0. Okay, so just x squared over x squared plus 0. Like that. Okay, so then that would be just 1, right? Because this whole thing is just the number 1, and the limit of 1 is just 1. It's a constant. Okay. Now, let me pick a different path. Let me pick the path along the y-axis. Okay, that would be the limit as 0 comma y approaches 0 comma 0, because again on the y-axis x is equal to 0, and that would give us 0 minus y squared, so that's a minus y squared, over 0 plus y squared. Okay, so that's -1, squared is +1, and the limit of +1 is +1. Okay, so here you might say, oh, well then I guess your hunch was wrong. And it sure looks that way, right? I tested it from this path, and it worked out just fine. And I tested it from this path, and it worked out just fine. The two paths agree. Oh, so at this point you say, well, obviously the limit exists and it's equal to 1, right? Well, no. I'm going to pick one more path. Because remember, there are other paths to the origin rather than just along the x-axis or the y-axis. What I'm going to do now is I'm going to come diagonally. I'm going to go ahead and pick the path where x is equal to y, coming to the origin along the diagonal. In that case, I would have the limit as x comma x. Right? Here x and y are the same, so instead of x and y, I'll just call them both x, as x comma x approaches 0 comma 0. Okay, so in this case, instead of replacing y's with zeros or x's with zeros, we'll replace x's with y's. Or I guess y's with x's. Look what happens now. That's going to be x squared minus x squared. Right, that's going to be an x. X squared plus x squared squared. That's 0. Right? That's numerator is 0. The denominator is not 0. 0 over something is 0. Squared is still 0. And the limit of a constant will stay constant. So there's a different limit along different paths. Here, if you picked other paths, you would probably get something different from either of these. So here, because yes, the limit along these paths exists, but they're not equal to each other. So here, this limit does not exist. Since the limit depends on the path, and it should not, it should be the same no matter what, this limit does not exist. So be mindful of the fact that if you check different paths, that will never tell you that your limit exists. The best you can hope for is that you can find something that's either undefined or different, and then that'll confirm that your limit does not exist. So you say, okay, so this is good for finding when limits do not exist. But how do you find when a limit does exist? Like, what if the limit's 12? How do you find that? Well, obviously one way to do it is if you can just plug it in. You say, yeah, but obviously plugging it in isn't going to always work. So what else can I do? Well, think back to Cal 1. What other techniques do you have for finding a limit? Well, one of them was simplifying the expression by factoring out common factors, by rationalizing numerators and denominators. So for example, let's go ahead and find the limit. And we'll go with the limit as x comma y approaches 2 comma 1 of x minus y minus 1 over the square root of x minus y, and then outside of the square root I'm going to have a minus 1. Okay. All right, here, unlike my hunch from before, here these were a little too different. Here these look very similar. I feel like things should cancel out. I feel like things should be easy to work with here. So I suspect that this limit does exist, which means I'm not going to waste my time with testing different paths, because I can never confirm if a limit exists by testing different paths. You might say, how are you getting this intuition? You keep saying, okay, I feel like that's going to happen, or this looks like this. Intuition in mathematics is an awful lot like intuition in driving. I've been driving in Houston for over a decade now. When I first started doing so, I was always surprised by the level of, let's say, aggressiveness that can sometimes be encountered. But after you see it enough times, you see every possibility. Right? You see the person who cuts you off from the left, the one who cuts you off from the right, the one who circles around to cut, who is on your left, circles around you, and then cuts you off on your right, and everything else in between. And eventually you just start to feel like, oh, I see what this person's doing, and I think I'll just move over a lane, right? Same thing happens here. There's nothing inherent that says, oh yeah, this is obviously what's going to happen. But once you do enough of these, you start to get a feeling for, oh, I've seen this kind of pattern so many times, and here's what happened last time, so I suspect that might be what happens this time. Basically, I look in the rearview mirror, I see the person in the very nice-looking car swerving back and forth, and maybe I take the next exit. Yeah. So here, I've seen enough times where the numerator and the denominator look very, very similar, and well, when that happens, I can usually simplify some stuff. So let's give this a try. Here, I'm going to pull a trick that we first see in Cal 1, and that's rationalizing. Here, notice if I try to plug things in. Now, of course, that should always be the first thing you do, because if you can plug it in and you get an answer, well, then you get an answer. So that should always be the first thing you try. But here, when you do that, if x is 2 and y is 1, 2 minus 1 is 0, 2 minus 1 is 1, square root is still 1, minus 1 is 0. So this is also 0 over 0, just like this one, but somehow it feels a little different. So right here, what we'll do is, I notice a radical in my denominator, and otherwise these look very similar. That's something that I remember from Cal 1. Whenever I have a radical in my denominator, it's often made simpler if I rationalize that denominator, which happened when you multiplied the top and the bottom by the conjugate of your denominator. So here, I'll multiply square root of x minus y plus 1 on the top and bottom. Like that. All right, so that's going to give me the limit as x comma y approaches 2 comma 1 of, well, let's see, if I multiply these, square root of x minus y times square root of x minus y, that square root of x minus y squared. The square will get rid of the square root, so that's just x minus y. If I multiply these, that's a positive root x minus y, but that's a negative root x minus y, which just gives me 0. Plus and minus gives me 0. And then here, negative 1 times 1 is negative 1. Oh, so if I multiply this out, I get this. But notice this was exactly what was in my numerator originally. X minus y minus 1. Oh, but now I've multiplied that times this. Well, yeah, but no one says I actually have to multiply it out. Because if I leave them separate, it's pretty apparent that the next step is I can divide these. And if I divide those, hey, there's no more denominator. And if there's no more denominator, this can't be indeterminate anymore. Here, this is equal to the limit as x comma y approaches 2 comma 1 of, this part's gone, and we're simply left with the root of x minus y plus 1. And this, we can just plug right in. Here, that'll give us 2 minus 1, okay, that's 1, square root of 1, well, that's still 1, plus 1, oh, that's got to be 2. So there we go. So go ahead and give these a try. Try the following two, as a matter of fact. Find the limit. Oh, let's see here. Let's try this one. Find the limit as x comma y approaches the origin of x plus y over x squared plus y. And then go ahead and also try this one. Find the limit as x comma y approaches, let's say 1 comma 1 of x minus y over x squared minus y squared. Okay? Note that both of these are indeterminate in form, 0 over 0, and likewise 0 over 0. So go ahead and give these a try and see what you can come up with. Once you have given these a try and come up with some results, go ahead and unpause the video and we can confirm those together. All right. For this first one, I noticed that this numerator and this denominator are, well, first of all, can I plug things in? No, I cannot plug things in. Okay, that should always be the first thing you try. The second thing I should try is, can this be simplified algebraically? Unfortunately, no. Now, this cannot be simplified algebraically, at least I don't think it can. But as I'm looking at it algebraically, I notice something here. This looks like 1. Right? Y over y is 1. So if x is equal to 0, this is the number 1. But over here, if y is equal to 0, that's x over x squared. That's definitely not the number 1. So I suspect that this limit will be non-existent because it's going to have different results from different paths. So for this one, I think I want to try things from different paths and see what happens if I can find that they differ or that some are undefined. This one, on the other hand, I look at this and that looks nice. That and that look just so similar. X over x squared, y over y squared. Things are approaching this. Yeah, this just looks like it simplifies the same no matter what I do. So here, I suspect this will give me a limit. So again, those are just hunches, but it's because I've seen problems like this so many times that I kind of recognize a pattern. This looks too different. I think something, quote unquote, bad will happen. I think something will prevent my limit from existing. So I think I'll check a few different paths. Here, this looks good. This looks so similar that I think things should work out nicely no matter what I do, which means I think I will find a limit. So let's try it. Here, let me try. Usually when I pick a path to try, I usually try going along one of the axes. If those don't work, then I'll pick something like x equals y, or whatever the case whatever I might come up with. But here, I'm going to just try along the, let's try along the x-axis, where y is equal to 0. All right, so let's go and pick the path. Along the x-axis. which means y is equal to 0. So here I'll get the limit as x comma y, x comma 0 approaches 0 comma 0. Here I want to be on the x-axis, so y is a constant 0, of x plus y, x plus 0, okay, so I'll just write x, over x squared plus y. X squared plus 0, I just write x. Oh, well that's just the limit as x approaches 0, right? Here there's no y anymore, of 1 over x. No, this is a result from Cal 1. This does not exist. Oh, so one of the paths, the limit as I approach the origin along this particular path does not exist. But unless they all exist and agree, well then I know for a fact the limit overall will not exist. So here this one does not exist. Right here. Which means I know for a fact that this limit up here does not exist. Okay. Here, again, you should always try plugging in first, but that gives you 1 minus 1 over 1 minus 1, 0 over 0. But in this case, again, I suspect this does have a limit. So picking different paths is not going to help, because no matter how many paths I try, I can never get them all. So instead what I'll do is I'll try to simplify, rationalize. Here I notice that I can actually factor this. After all, this is the limit as x comma y approaches 1 comma 1 of x minus y over x minus y times x plus y. Notice that your denominator is the difference of squares. Oh, but if I factor it that way, I now notice that here, as long as these are not both 0, which they're not, right? You're not at 1, 1, you're just near 1, 1, then these are not identically 0, which means they can be divided. So now this gives me a much simpler limit as x comma y approaches 1 comma 1 of 1 over x plus y. And now I just plug that in. 1 plus 1 is 2. So here my limit is 1/2. And that makes us happy. All right. This brings us to our next definition. We've defined a limit. Now let's define something directly related to those limits. Let's talk about continuity. Let f be a function of two variables. Oh, I guess I can just write it then. Let f be a function of two variables. So f of x comma y. That is defined on a region, let's say on an open region, which we'll call R. Let some point x naught comma y naught be in R. So you've got your function defined on this open region, and here you've picked some point from this open region. Then the function f is said to be continuous at that point if and only if the limit as x comma y approaches that point, x naught comma y naught, of f of x comma y is equal to f of x naught comma y naught. If f is continuous, at every point in that region R, then f is said to be continuous on R. What the definition is saying is, hey, if you can get the limit by just plugging things in, then it's continuous at that point. Some examples. Let's just go back to these limits that we had over here. Here, we could not plug in 0, 0. And in fact, you don't even get a limit at 0, 0. Now, that is a little different from what we see over here. Here, you could not plug in 1, 1, because that was undefined, and 2, it was indeterminate, but you still were able to get a limit. And in fact, you were able to get a limit by plugging it in. It's just you weren't able to plug it until you simplified. So when we have something that's continuous, okay, great, it's continuous. But if something is not continuous, it seems like we can separate it into two categories. Not continuous and just that's it, and then not continuous, but if we play with it, then we can plug things in. All right? So our categories are, let's see, here, this one, we were able to just plug it in. So here, this is continuous. The very first example we did, this is continuous at 1, negative 1. It's probably continuous plenty of other places, but it's certainly continuous at that point because you were able to just plug it in and you got your answer. Here, not only can you not plug it in, but in fact, there's no limit at all. Okay, so then here, this is not continuous, but whenever something is not continuous, you can also say it's discontinuous. But here, this is the kind of discontinuity where you never get a limit, no matter what. Like you can't even simplify your way to making this work. So this is not continuous, or you can say discontinuous at 0, 0. And whenever you have something like this where, yeah, it's not continuous, you can't plug it in, but also you can't even simplify it so that later you can plug it in, this is called a non-removable discontinuity. Non-removable discontinuity. Okay. Here, this one, it looked same thing. We could not plug it in to get an answer, nor could we simplify it. Here, the limit just does not exist. So again, this is not continuous and non-removable. Not continuous at 0, 0, and it's non-removable. Okay. This one, okay, you could not just plug in 2, 1, right? Because it would be indeterminate. But in this case, you can simplify your way out until eventually you can just plug in the numbers. So this is still not continuous at 2, 1. But it has what's called a removable discontinuity, meaning you can simplify your way to get something that's easy enough where you can just plug things in. So this is discontinuous. Or let me just keep with the same language. It's not continuous. They mean the same thing, discontinuous or not continuous. This is discontinuous at 2, 1, but it is a removable discontinuity. You can remove it. You can get rid of it. Removable discontinuity. Okay, let's see. 1, 2, 3. Okay. And then over here we have these two other ones. What do you think? What's this one? Well, the limit does not exist, so you can't plug it in, nor can you fix it so that you can plug it in. Okay, so this is not continuous. At 0, 0. And not only is it not continuous, it's a non-removable discontinuity. This one, well, you could not plug it in. Okay, so this is also not continuous. Oh, but I was able to simplify it so I could plug it in. Okay, it's not continuous, at least at first, but you were able to remove the discontinuity. So this one is not continuous at 1 comma 1, but the discontinuity is removable. Those were good examples. I didn't have to go back and write anything. I should come up with examples like that more often. I don't have to go back and redo any examples. We just go back and do the ones we already looked at. I got to remember that. Now, from evaluating these past few limits, we see that many of the properties that we're used to for limits in Cal 1 for functions of a single variable still apply. It turns out we can extend that quite a lot more. Many of the properties, in fact, just about all of them still apply. So let's see what those look like. Let's remind ourselves of what they are, and here we have a theorem. So let's begin with a couple of functions of two variables and a scalar. Let f and g be two variable functions. So f of xy and g of xy. That are continuous at some point x naught comma y naught. So f of xy and g of xy, both of them are continuous at this point, whatever it might be. And let's let k be a constant. Just some real number. Okay? Then the following statements are true. Then the following statements are true. K times f of x comma y. 2. F plus or minus g of x comma y. 3. F times g of x comma y. And 4. F over g of x comma y are all continuous at x naught comma y naught. So if both of them are continuous here, then you can take one of them and multiply it by any constant. You can add the two of them, you can subtract the two of them, multiply the two of them, or divide the two of them, and all of those results are still continuous at this point. The only stipulation is this last one. You have to make sure that that one is defined, which means that your g is non-zero, where g of x naught comma y naught is not 0. Because of course it's 0, that's undefined, and so it's not continuous, it's not anything, it's nonsense, it's gibberish. Here I'll give a partial proof of this. I'm only going to prove number 2. Why not the rest of them? Because all the rest of them are exactly the same, and well, frankly, it gets a little boring for people to for me to say it and for people to listen to it if all of them are pretty much the same. So here I'm just going to give the proof of number 2, and the rest are omitted due to, well, frankly, all of us having better things to do. So let's go ahead and say partial proof. And we'll only look at number 2. All right, so let's begin by assuming that, as we were told, f and g are continuous at x naught comma y naught. All right, so by definition, we have that the limit as x comma y approaches x naught comma y naught of f of x comma y equals f of x naught comma y naught. After all, that's what it means for f to be continuous at x naught comma y naught. That means if you take the limit, you just plug in that point. Okay. Thus, also by definition, that means that for all epsilon greater than 0, there exists a delta greater than 0. And here I'm going to call this delta 1 because I'm going to have another delta later in the proof. Delta greater than 0 such that zero less than the square root of x minus x naught squared plus y minus y naught squared is less than delta 1. Implies that the absolute value of f of x comma y minus f of x naught comma y naught is less than epsilon. So here I've just written the definition of what this means. What does it mean for this limit of f to equal to this? Oh, that means that as long as these two are within a delta neighborhood of each other, that implies that this and the proposed limit are within any epsilon that we choose. Likewise, because g is also continuous, you can also say, well, the same thing except with g in place, right? So here we can say likewise, for all epsilon greater than 0, there exists some delta. Well, now, that doesn't have to be the same as this delta, so I'll call it delta 2 greater than 0. Such that, yes, I did just misspell the word such. Such. Interesting. Such that 0 is less than the square root of x minus x naught squared plus y minus y naught squared is less than delta 2, implies that the limit for g is equal to g with that value plugged in. Or in other words, the absolute value of g of x comma y minus g of x naught comma y naught is less than epsilon. Okay? Now, consider, and here I'm going to just work with the sum. I'm not doing the whole proof. Just now consider the limit as x comma y approaches x naught comma y naught of f plus g of xy. Okay? Well, we want to show that this is continuous also. In other words, we want to show that this has the limit that's equal to just f plus g of x naught comma y naught. So by definition, that means we need to find some delta that works for this one. We found a delta that works for f. We found a delta that works for g. So we need some delta that works for f plus g. Well, yeah, but this one works for f. And this one works for g. So what if I just grab the biggest one? Because here these are probably not the same. So let's say this is 0.1 and this is 0.3. Well, then wouldn't 0.3 work for both of them? So grab the biggest one. Oh, but it's not going to be good enough because here it's not saying either one. It's actually the sum of both. Okay, so grab the biggest one and double it. Right, that way, that'll be big enough to cover one of them and bigger, more than big enough to cover the other one. So here, let delta 3 equal to double the max. I'm not sure if you're familiar with this notation. Max delta 1, delta 2. That just means out of those two, pick whichever one's biggest. That's what max of this means. Just out of those two, pick the biggest one and then double it. We'll call that delta 3. Then, for all epsilon greater than 0, we have delta 3 such that 0 less than square root of x minus x naught squared plus y minus y naught squared is less than delta 3, implies that the absolute value of f plus g of xy minus f plus g at x naught comma y naught is less than epsilon. But by definition, that means that the limit as x comma y approaches x naught comma y naught of f plus g of x comma y equals that function there, or rather equals that limit there, f plus g at x naught comma y naught. So that means if you began with the assumption that f and g are continuous, then by definition, thus f plus g is continuous at that point as well. And there we go. Basically, okay, we know we can find delta for the first one. We know we can find delta for the second one, so then just pick the biggest one and double it, and you're good. The same proof holds for all of them, with minor variations. So because the proof holds for all of them, that's we're not gaining too much more insight by proving the rest of them, so we'll say this suffices. The rest of the proof is omitted due to, as I said earlier, everyone having something slightly better to do. In fact, the following theorem will also be omitted for the exact same reason, the proof, I mean, but the result is worth stating. Theorem, we see that we have two functions being continuous at a point means that their sum, product, and quotient are all continuous at that point. There is one more operation that you can have of functions, and that is the composition. So here, theorem, let h be continuous at x naught comma y naught and let g be continuous at h of x naught comma y naught. Then g of h of x comma y is continuous at x naught comma y naught as well. Or in other words, meaning if you take the limit as x comma y approaches x naught comma y naught of g of h of x comma y, you'll get g of h of x naught comma y naught. The proof of this one is omitted for the exact same reason. It'll look just like one of these. So instead, let's go ahead and look at some examples. Here, proof. I'll write one thing that you'll see in a lot of math books, upper level math books, and that's the proof is trivial. That's a sort of a bit of a joke. It's called proof by intimidation. This is not actually what it's called. However, it's a bit of a joke among mathematicians that whenever someone writes the proof is trivial, that means it's also called proof by intimidation, meaning, oh yeah, this is trivial, this is easy, obviously everyone sees it, right? And the idea being that anyone who doesn't see it doesn't feel confident enough to say, no, can you show us anyway? So this is often called proof by intimidation. We're intimidating you into saying, oh yeah, no, trust us, this is easy, and no one wants to say otherwise. In reality, no, this is not easy, but it is so reminiscent of one of the proofs like this that it doesn't really provide any more information. So if you understand this one, you'll understand the other one. If you don't understand this one, the other one is just a repetition of the same thing anyway. So here we'll gain a little bit more, I think, by looking at examples of this. Should anyone need a proof of this, please let me know and we can go through that together. But for the sake of this lecture, let's look at some examples instead. So here, let's go ahead and discuss the continuity. And evaluate the limit. Let's take the limit as x comma y approaches 1 comma 1 of x over the square root of x plus y. All right. So here we can take this as a few different smaller functions. Here clearly the limit as x approaches 1 is continuous, because thinking back to Cal 1, the limit of any polynomial expression, and x to the first power is technically a polynomial, that is clearly continuous. All right, so here clearly x, which is a polynomial, is continuous at 1, 1. Because all polynomials are continuous everywhere. Okay. Here you can even say just at 1, since that doesn't even have a y value. Okay. Now, the square root of x plus y. This is continuous for anything that makes the argument positive. Oh yeah, but 1 comma 1 that's going to make that positive. That's going to be 2. Right? So here clearly 1 is a 1, which is a polynomial. Sorry, clearly x which is a polynomial is continuous at 1. Okay? Here, this is also continuous. At 1 comma 1, because you're taking the square root of a positive polynomial. Obviously, the polynomial is going to be continuous anywhere, and if you're taking a square root, as long as it's positive, that's a perfectly well-defined function. So here you're taking the square root of a polynomial that is positive at 1, 1. Okay, so each of the components is continuous at that point, but here this is division. And we did have a third stipulation for division. Oops, that's the wrong page. Here we go. For division, we said, yeah, they both have to be continuous, the numerator and the denominator, at that point. But finally, we also have to say that this is not equal to 0 at that point. Okay, so let's go ahead and check that as well. So normally we don't have to check the numerator, and normally we don't have to check the two different functions that are put together. But since this is put together as a quotient, we now need to check that the denominator is not equal to 0. Oh, but here it's definitely not, at least not around 1 comma 1 here. Square root of x plus y is definitely not 0 at 1 comma 1. In fact, it's not 0 for a neighborhood around 1 comma 1. Okay, so that means that you have, clearly this is continuous at 1, 1. This is continuous at 1, 1, and the denominator is not 0. Oh, so that must mean that my overall expression is also continuous at 1, 1. So x over square root of x plus y, really I should say the function f of x, y equals this, is continuous at 1, 1 as well. But as we learned in the definition, if something is continuous, that means I just plug in the numbers. So here, that limit will equal to 1 over the square root of 1 plus 1. In other words, it's equal to 1 over root 2. And because this book likes to rationalize absolutely everything, you'd probably see it as root 2 over 2. And there we go. Let's take a look at one more that involves a composition. Let's take the limit as x comma y approaches 2 pi comma 4 of the sine of x over y. Okay. All right, so composition, one function inside of another, a rational function inside of a sine function. All right, well, clearly x over y is continuous at 2 pi comma 4. And you say, why is that? Well, for the same reason that we had above. So we know x and y are continuous anywhere. Continuous everywhere, because again, they're polynomials. And as we see in Cal 1, polynomials are continuous for all real numbers. Okay, since y is not equal to 0 at or even near 2 pi comma 4, then both components are continuous and the denominator is not 0, then x over y is most certainly continuous at 2 pi comma 4. Okay? This is what mathematicians, when we say clearly, if you think about it for maybe 10 or 15 minutes, absolutely. There's a joke about mathematicians where a professor is explaining something at length and he's going on and on about something. And at one point he says, so clearly the following limit is equal to 73. And one of the students raises their hand and says, I'm sorry, Professor, you say that limit is clearly true? And the professor says, yes, of course. And the student says, I'm sorry for my ignorance, but I don't see that. Could you show me how that limit is 73? And the professor says, well, of course. Obviously it's, oh, well, let's see. And the professor starts to writing on the board, and then he seems to get stuck, and he says, here, let me see. So he grabs some paper and he starts scratching things out, and people are sitting there, and 10, 15 minutes go by, and he says, give me a moment. So then he runs out of the room, and he comes back about 45 minutes later holding a book and several scratches of paper going, yes, it is clear, it is obvious. So to mathematicians, sometimes clearly or obviously is maybe not what most people would think of as clear or obvious. So I will occasionally use the word clearly because, well, it's hard to get away from that word. It's just something that you get used to after many, many years of math. But I will do my very best never to say clearly and then leave it at that. Here, clearly. Why? Because of what I've said in the last 10 or 15 minutes. Clearly. All right, so now, because this is clearly continuous, now let's consider the composition. Note that because x over y is continuous at 2 pi over 4, then that means that the limit as x comma y approaches 2 pi comma 4 of x over y is equal to, well, because it's continuous, we can just plug in the numbers. That'll be 2 pi over 4. Or in other words, pi over 2. But now, as we clearly see in our most recent theorem, as long as the outer function, in this case our sine, as long as the outer function is continuous, g is continuous at h of x naught comma y naught. Okay, so it's continuous at, we've plugged our point into the inner function. Oh, here we go. We took our point, plugged it into the inner function, we got pi over 2. So now we need to check that the sine function is continuous at pi over 2. Oh, but we know the sine function is continuous for all real numbers as well. We learned that in Cal 1. Since the sine of some argument is continuous for all real numbers, the domain of the sine function is all real numbers, at all real numbers, which of course includes pi over 2, then that means that this is continuous. Then sine of x over y is continuous. At the point in question, 2 pi comma 4. And then the second part of our question was evaluate the limit. Well, that is continuous at this point, so go ahead and plug in the point. This will equal sine of, again, 2 pi over 4, which is sine of pi over 2. And the sine of pi over 2 is maybe a little anticlimactic, is 1. So that brings us to our results and to one final definition. Note, everything that we've talked about here has been of functions of two variables, f of xy, g of xy, h of xy, or additions, subtractions, multiplications, divisions, or compositions thereof. However, you can extend this into 3 dimensions or more. You could talk about functions of x, y, and z, or x, y, z, and w, or x1, x2, x3, x4, x5, x6, and x7 if you like. You would simply have to extend what you mean by an open ball. Here, on a number line, there's an open interval around a point. On the plane, you have an open neighborhood, an open disk around your point x naught comma y naught. If you wanted to extend this into R3, into space, well, then you would have a point x naught comma y naught comma z naught, and instead of having an interval or a circle, you would have an open sphere around that point. And if you were to go into 4 dimensions, you'd have an open hypersphere, 4-dimensional sphere, 5, 6, 7-dimensional spheres. You would have to adjust what you mean by an open neighborhood around that point. Otherwise, all of this applies in any number of dimensions. So we'll close this section with a single definition, which we will not utilize now, but it does show that this can be extended as much as we like. Let f be a function of 3 variables. And of course, we can extend that even further, but for now we'll be satisfied with 3. Let f be a function of 3 variables. Okay. Let R be an open region in space. Okay. You may have noticed I mentioned a word a moment ago. I said R3. You may wonder, what was R3? Is that like this R? Whenever you talk about the real number lines, whenever you talk about the real numbers, the numbers on the real number line, you may have seen this symbol before. It's a R with like a little double back. This represents the real numbers. Okay. Whenever you have the plane, Well, we can call it the plane. We often call it the XY plane, or any other number of names, the Cartesian plane and so forth. But another way to call this is, well, this is a real number line, and you've crossed it with another real number line. So one way of expressing the plane is to call it R cross R. There's a little more to explain here, but basically you're crossing one with another. That's actually not quite true where the name comes from, but suffice it to say that this is a way of expressing the plane. When we say R cross R, we also sometimes call it R like this. It looks like, R times R is R squared. Again, not quite right, but that is what in the notation is at least supposed to look like. This is not all called R squared, though. It's usually called R2. Why? I don't know. That's just what it's called. Here, when you have three number lines crossed together, you can call it R cross R cross R. Notice we're not actually saying we're crossing them as in, the word like, oh, this comes across this. When we say cross, we're talking about what are called direct sums and direct products. That's something from higher level courses. But suffice it to say that when you have three number lines that are independent of each other, all in the same system, you can call it R cross R cross R, which is often referred to as R with a little third power like that, and it's not usually called R cubed, it's usually called R3. So the real numbers are often just called R, the plane can be called R2, and space can be called R3. So you heard me say that a moment ago, and I just wanted to explain that to try to get that clarified a bit. That had nothing to do with this R. This R is just the name of a region. Space is often called R3. That's just another name for it. All right. So let f be a function of three variables. Let R be an open region in space in R3. Finally, let x naught comma y naught comma z naught be a point in the region R. Then f is said to be continuous at the point x naught comma y naught comma z naught if and only if and, well, I think you can see what's coming. It's going to be the same definition with a third component. If and only if the limit as x comma y comma z approaches x naught comma y naught comma z naught of f of x comma y comma z is equal to f of x naught comma y naught comma z naught. Not exactly surprising given how we've seen extensions into space happen in previous sections. We simply add the next component up. If f is continuous, at every point in R, then we say f is continuous on R. And there we go. So that brings us to the end of our section. If there's any questions, comments, or problems, please make a note of those, reach out, and let me know. Otherwise, I hope everyone has a nice day.